Okay.
For the last question on extra credit, I just wanted to make sure.
We will teach Caleb about this. We will use for that last problem, we need to use a theorem which is called Bayes Theorem. Okay. And our main goal this week is to use this theorem to see a special classifier which is called naive Bayes Theorem. We will explain why it's called naive. Then my goal today is to review the concept of Bayes Theorem because some of the students are familiar, some of the students are not. Then we will give time to all of you to finish it and return it on Thursday. That's my plan. Then after explaining about Bayes Theorem, then we can answer question about the last problem better. Then please let me explain a little bit about Bayes Theorem today. Yeah. Then we will talk about the last problem. I'm sure that we will, if we explain about the Bayes Theorem, you will find last problem very doable.
Yeah, no, I have an answer. It's just I wanted to double check. Yeah.
Oh, nice.
Yeah. So
what is your major?
Aerospace engineering.
Okay. Then
I took statistical machine learning.
Oh, okay. Did you take machine learning and statistics? Why you take? I'm happy that you have taken this course, but I'm just curious why you have taken this course.
So my major, my research topic is applying machine learning to fluid simulation.
Oh.
And so I do need like a heavily practical experience, and my starting out with machine learning was entirely self-taught with re-implementing a master's student's work on.
Oh, okay.
So I took statistical machine learning.
You have seen this Bayes Theorem.
Yeah.
Nice.
Yeah. So I just wanted to make sure that because you know that the blue ball was selected, that it's just the probability of which box.
Mm-hmm. Yes. And in this case, the reason that we need Bayes Theorem because we need to switch the one which is given and the one which is wanted.
Yeah.
And that's the reason that Bayes Theorem here is helpful.
Yeah, because I started to write out the probability of like this box is selected, the probability of the blue ball, and then I just realized it's
this one.
You just throw everything out.
Exactly.
Yeah.
Exactly. Okay, good morning everyone. Thank you for coming to the class. For this week, my goal is to explain about one classifier which is called Bayes classifier. In order to understand actually naive Bayes classifier, we'll explain why it is naive, because it is based on a very naive assumption, very unlikely assumption, and it is based on a very famous theorem in statistics which is called Bayes Theorem. Some of you may be familiar with Bayes Theorem, some of you may have not seen it before. Then I decided to give a very fast review about probability theory and these concepts in probability theory that we need for Bayes Theorem. Then you will finish extra credit 1 that I gave you last week at home, and we will collect this extra credit on Thursday. Then on Thursday, if you look at that extra credit, you can see that there are some problems about probability theory. Then today we will review probability theory concepts from probability theory that we need for this class very quickly. Then we will explain about Bayes Theorem. Then at home you will complete these problems that we have in the extra credit number 1 about probability theory. And please return your work in class on Thursday. Your work will be graded and your grade will be posted on Carmen. Questions, comments? Okay. So then let's dive in. So what we want to explain about? First, we want to explain about probabilistic agent. We want to see that why concept of probability is needed. Then we will explain some basic notion that we have in probability theory. Then we will explain about two concepts, period and posterior probabilities. And we will see that especially for Bayesian statistics, this concept of period and posterior probabilities are very helpful. Our main goal is not to teach Bayesian statistics. Our main goal mostly is to teach Bayes rule or Bayes theorem. We will explain about Bayes theorem, and then we will solve one problem by solving this problem, I'm sure that you will get a good idea about solving the problems that we have in the extracurricular sheet. Then we will explain about what Bayes classifier means, and we will solve one problem. I should warn you that the homework that we have for this week, we post the homework this week on Friday, and you have 1 week to finish it. It's a little bit hard homework, harder than homeworks that we had up to now. Up to now, we had 3 homework assignments, and homework number 4 that we will post on Friday, and you have 1 week to finish. It is a little bit harder. I will explain about this homework, and we will explain what should be done in this homework. I have also graded your homework 1. Grades are uncommon. Please see if something is wrong, please let me know. And that's what we want to do this week. Questions, comments, anything? Perfect. So hope you do not feel that we are going this stuff fast. My feeling is that because we want to teach this stuff fast and reach to something which is more interesting, then let's start about probabilistic agent. In AI, in artificial agents, we have artificial intelligence. We have 2 different types of several agents, but one agent that we want to talk about is agent that you have some uncertainty about the environment regarding to that agent. Let me explain about this. Maybe some of you have seen this before, maybe some of you have not. When probability makes sense, in what scenario we can talk about probability? Probability makes sense if there are some uncertainty around. If you have the situation that everything is certain, then talking about probability doesn't make sense. Let me give you one funny example. Election is a very good example. We have different situations. In countries like my country, there is nothing uncertain about election. It means 2 years before election, everybody knows who will win. People sleep well. Nothing to worry about. In countries like my country, election, if somebody asks this question, what is the probability that Ali will win the election, is absolutely 0. See, because winner is now, right now, 2 years before election, winner is now. Then people are happy. But there are some countries that winner is not now in the election. In this kind of cases, talking about probability makes sense. You can say that what is the probability of candidate 1 win? What is the probability of candidate 2 win? See, these kind of questions make sense. Then always when you talk about probability, you are talking about uncertainty. If no uncertainty around, then talking about probability doesn't make sense. Then everything that we have in probability theory, everything that you have in statistics, if you took courses in statistics, I'm sure that you have seen it. Everything that we have in statistics is about probability, and everything which is about probability, in some case, concerning about the concept of uncertainty. If no uncertainty around, like election in my country, then nothing to worry about. Therefore, in this case, probability doesn't make sense. And these kind of situations that they have some uncertainty are called stochastic. Therefore, we have 2 different types of agents. For some agents, which are called the stochastic agent, which means there are some uncertainty in the environment. For some agents which are not stochastic, it means that no uncertainty in the environment. Therefore, it is important to make sure that everybody understands that when we are talking about probability, we are talking about some uncertainty. Now, if we want to have a definition, very easy definition of probability, let's see what probability means. Probability gives us a tool to compare the different events. It means you have some events in the environment that there are some uncertainty in that environment, and if you want to see in what way 2 events can be compared. Therefore, probability is a tool, is a number which gives us the ability to compare the different events. And here, as you can see, probability is a number which is between 0 and 1. 0 means therefore events that never happen. 1 are for events that always happen. Or sometimes we say that for the cases for events which are always false, we use 0. For the events that are certain, means that always they are certainly true, we have 1. These are some basic concepts about probability and meaning of probability. If you want to see more formal definition of probability, we have to consider the definition of sample space. As I explained, when we are talking about probability, it means that some uncertainty involved. Then, when you have an experiment for which there are some uncertainty, people can define a set which contains all possible outcomes of that experiment. Such a set is called sample space. We can, some of them be familiar with this, we can have sample spaces which are finite, we can have sample spaces which are not finite, we can have sample spaces which are countable, we can have sample spaces which are not countable. Depending on what type of sample space you have a different type of statistics. You know that in statistics we have continuous and discrete sample spaces. Discrete means sample spaces which are finite or countable, and continuous means sample spaces which are not countable. We hardly ever talk about sample spaces which are not countable. Mostly in this class, we are interested in sample spaces which are finite or countable. Okay, so here we have one example. For example, if you roll 2 dice, then if you want to list all possible cases in a set, then this sample space can be found. Here, as you can see, in this sample space, there are 36 elements. These 36 elements shows us all possible outcomes. And you can say 1, 1, 1, 2, 1, 3. It means that, for example, we have for die 1, we have 1. For die 2, you have 2. And same thing for 6, 6. For both, we have 6. Then all possible outcomes have been listed in this set. And the set that we have here is the sample space. So after defining sample space, we can define the concept of event. An event is any subset of sample space. And when you have a sample space, if you choose one subset of that sample space, you define an event. For example, here we have the sample space phi omega, then you can define phi, which contains just 2 elements. These 2 elements are cases that 2 dice add up to element. And here, as you can see, if you want to list cases that when you add numbers which are showing on each die, then you will get element, then you can have these outcomes, 5, 6, 6, 5, so all possible outcomes. Then that's an event in the sample space of rolling 2 die. So any questions, any comments? Okay. Again, if you feel I'm going fast, please stop me, because I just want to make sure all of us are in the same page. Some of you have seen this stuff, some of you have not. So every element that we have in the sample space, we can define a chance or probability. Probability is a number that you assign to every element in the sample space. Not every number can be assigned to elements in the sample space. The number that you assign to the elements in the sample space should be between 0 and 1. And when you add them up, you should get 1. It means that after assigning numbers to elements that you have in the sample space, if you add all of them, you should get 1. These are 2 properties which should be satisfied by the numbers that you assign to the elements of the sample space. So, for example, for the example of rolling 2 dice, one way to define weights, one way to define probability on elements that we have in the sample space is considering the equal elements to equal numbers to the elements that we have in the sample space. In this case, we can say 1 over 36. And as you can see, in this case, we are assuming that every outcome that we have in the sample space of rolling 2 dice has the same chance. A situation like this is called a fair experiment. It means that you assume that all outcomes have the same chance to occur, and the same chance that we have is 1 over 36. Okay, after defining these probabilities to the elements that we have in the sample space, we can define the probability of an event. If you assume phi is an event, probability of that event is defined as the sum of probabilities of elements belonging to that event. Here phi is an event. You have a sample space that is weighted, means that every element that we have in the sample space contains a probability. Means a probability is assigned to every element in the sample space. Then when you want to define the probability of an event, you just need to add the probability of elements belonging to that event. So, for example, if we come back to the example of rolling 2 dice, then you can see that if you want to find the probability of total equal element, then you just need to add the probabilities of elements belonging to that event that we explained about. As we explained, if we assume that every element in the sample space has the same chance, then we can say that that equal chance is 1/36, then we add them, we will get 2/36, and if you simplify fraction, then you will get 1/18. That's very easy example. Okay, questions, comments? Question? Okay, if we have a sample space, that every element in the sample space has the same chance, the formula for probability that we had in the previous slide can be adjusted in maybe more practical way. Remember, please, again, I'm talking about sample spaces which are finite. You have a sample space which is finite. You assume that every element that we have in the sample space has the same chance. Then, if you assume phi is an event in the sample space, then when you want to find the probability of phi, you just need to find the size of phi and divide it by size of sample space. Then this number will give you the probability of phi. Please remember that this formula can be used for the case that the chance of each outcome in the sample space is the same. It means we have the equally likely outcomes. When we have the same chance for every element that we have in the sample space, then when we want to find the probability of one event, you just need to find the size of that event and divide the size of that event by the size of sample space. Then you can find probability very easily. That's a very famous formula. We will use this formula. If we come back to the example of rolling 2 dice, and if we want to find the probability of total sum is 11, then again, as you can see here, the number of elements that we have in the event is 2. The number of elements that we have in the sample space is 36, and when we divide them, we get 1/18, and that's the number that we got by the original formula in the previous slide, and that's what we expect. Okay, so questions, comments, again, if you feel I'm going fast, please let me know. My feeling is that most of the students are familiar. I just want to make sure all of us are in the same page. Okay, so we have some examples here, very easy example. In the Excel credit sheet, you have the similar problems. In a lottery, players win a large prize when they pick 4 digits that match in the correct order. 4 digits selected by a random mechanical process. Again, you can see that when you want to talk about probability, something random should be there. If there is nothing random, if there is nothing uncertain, then talking about probability doesn't make sense. So then here in this case, as you can see, we have the machine which chooses these digits randomly. A smaller prize is 1 if only 3 digits are matched. What is the probability that the player wins the large prize? And what is the probability that the player wins the small prize? So then here we have 2 situations. In the first situation, when we want to find the probability of the case that we get the large prize. When we say that large prize, here in this case it means 4 elements match. And when we say we want to get the small prize, means that just 3 digits match. Here you are choosing 4 digits, and these 4 digits are chosen randomly. After choosing these 4 digits, we want to see that if 4 digits match, we get a large prize. Otherwise, we will get a small prize. So the only thing that I want to explain is that we need techniques, we need tools to count the number of elements in the sample space and the number of elements in the event, because we want to divide them. So I just want to explain a little bit about, again, Maybe for some of you it's boring, for some of you it's not, but I just want to make sure all of us understand this. I just want to explain a little bit how this counting can be done here. So, okay, so I want to choose a number with 4 digits. So when you want to find a number with 4 digits here, these are the digits of this number that I have. I will find the number of cases that each digit can accept. Then we will talk about a principle which is called the principle of product. For example, for the first digit, how many cases we have for the first digit? 10. For the first digit, there are 10 cases because you have 0, 1, 2, go to 9. Then we have 10 digits here. What about for the second one? For the second one, see, that is a good point. Someone can say that 9 here, but here, remember that the digit which has chosen for the first one, that one also can be chosen for the second one. Therefore, again, for the second one, we have 10. For the third one also, we have 10. For the last one also, we have 10. Here, I do not care if you have 0 at the starting. It means that this one also is accepted. 0, 2, 3, 1. That one also is accepted. And I do not care if I have the repeated digits, means 0, 1, 1, 1 is okay. Therefore here, for each digit, we have 10 possibilities. There is one property in statistics which is called the principle of product, which tells us if each of these can be done with 10 different cases, when you want to see in how many cases all these digits can be made, you just need to multiply these values. When you multiply these values, you will get 10 to the power of 4. This is the number of outcomes that you have in your sample space. Therefore, all possible outcomes that we have, in other words, the size of the sample space is 10 to the power of 4. So, now let's talk about 5. Say 5. I'm talking about 5 for the large price. And then we will talk about 5 for the case that we have small price. So then in the solutions that we have here, then now we know that this 10 to the power of, how we get this 10 to the power of 4 ways. But when you want to find the probability for the large price, because for the large price, all digits should match. Then how many cases we have? Just one case. Because as you can see, we have one specific number, and for that specific number, there are just one possibility. Therefore, each digit should be equal to that specific case. Suppose, for example, your specific number that you will give the large price to the winner is, I don't know, 2314. Then when you have 2314, then for the first digit, you have just one possibility, which is 2. For the second digit, you have just one possibility. For third, the same. To fourth, the same. Therefore, you have just one outcome. For the case that you want to give the largest price. In this case, probability is 1 over 10,000. Okay, so what about for the smaller price? For the smaller price, as we explained, just 3 digits should be matched. Therefore, for 1 digit, we have the freedom. Here, why we have the, okay, then the number of outcomes that we have in the sample space is 10,000. What about the number of outcomes that we have in the event? Event means our favorite case. Our favorite case means the case that 10 digits match, for the case that 10 digits match. So then we know that 10 digits match and another digit, the fourth digit, is not necessarily matched. In this case, as you can see, since one value has been chosen, therefore, the possibility that we have here is 9. And we can say 9 for that. Then this 9 can be everywhere. It means that it can be at the beginning, can be at the second digit, third digit, or fourth digit. That's the reason that here we have 4 times 9. 4 times 9. So, and we calculate this and we got this. As you can see, explain this. I'm not sure how much this explanation here makes sense. Then exactly one digit must be wrong. These are the other. We should not make mistake. Therefore, when we say that exactly one digit should be wrong, then it means that for one digit, you should get the number other than that specific value. Then that specific value cannot be chosen, then there are 9 possibilities. I've seen that why we have 4 times 9, because these digits, which can be wrong, it can be in the first digit, can be in the second digit, can be in the third digit, or can be in the fourth digit. That's the reason that we have 4 times 9. Okay, so questions, comments, anything, any questions? Questions? Okay, so we have another example here. So what's the probability that a person picks the correct 6 number out of 40? I just want to explain about one notation. I'm sure that most of you are familiar with notation. If you are not familiar, I want to explain about this notation. See, I have 40 number and I want to choose 6 out of them. Here we have 6 numbers, and we have 40 number. I want to choose 6 number among these numbers. So there is a formula, this notation, sometimes people write C46, sometimes people use this notation. This notation in a statistics is called combination. What this notation means whatever that you have on the top factorial, whatever that you have on the bottom with factorial, and you subtract top from bottom and again with factorial. So you don't need to memorize it. I'm sure that you know that in every calculator these days, you have this combination formula. They just need to give the number to the calculator and get the answer. But the only thing which is important, what can be calculated by using combination? When you use combination, you are calculating the number of days that 6 elements can be chosen out of 40. But here order doesn't matter. Again, very quick. In statistics, when we want to count the number of elements that we have in the sample space, usually 2 scenarios can happen. Sometimes order matters, sometimes order doesn't matter. Then when order doesn't matter, we use this formula of combination. You know that if order matters, the 6 factorial is not written on the top. And in the case that you have selecting m element out of n elements, this formula can be used. In this case, you want to select 6 elements out of 40, therefore you can use this formula. And the probability here can be evaluated by 1 over 40 over 6. The formula of combination. Again, if you have seen it and you find this stuff boring, I'm sorry, just want to make sure all of us are on the same page. And one example of poker, we have another example on this slide. In the extracurricular that you have, and we collect this extracurricular on Thursday, you have the similar problems. Just I want to explain one example, then we will teach something new, but I just want to make sure all of us are familiar with terminology that we have in the extracurricular. So what we want to do, find the probability that a hand of 5 cards in poker contains 4 cards on 1 card. So again, I'm not sure how much you are familiar with poker and you are familiar with cards. In cards like this, we have 52 cards, and these 52 cards is divided into 4 classes. Each class contains 30, and we have names on these cards. So then there are 52 cards totally. You want to choose 5 cards out of 52 cards. as we explained in the previous slide, when you want to evaluate the number of cases that 5 cards can be chosen out of 52, the combination formula can be used. And the number of cases that 5 cards can be chosen out of 52 cards can be evaluated by using this formula. Okay, so what about, that's the number of cases, that's the total number of cases that we may have. More precisely, that's the number of elements belonging to the sample space. Next step, what about the number of cases that we have in the event? More precisely, what is the number of our favorite cases? Our favorite cases are those that in our hand, which contains 5 cards, we have 4 cards of one kind. Instead of, the kinds we have named for them. For example, we have, I don't know, heart, we have a spade, we have diamond, something like this. Then when we say that one kind, then you need to understand the meaning of one kind. Let me explain. So the number of hands of 5 cards with 4 cards of one kind can be found by using this formula. See, you are choosing 1 out of 13, 4 out of 4, 1 out of 48. So let's explain, let's understand together one by one these numbers. For example, how I got 1 out of 13? What is this 13? What is this 13? Now, please, what was your name, my friend?
Of specific kind.
Yes.
Specific kind.
For example, when you say specific card, what do you mean? Can you give me one example?
Like heart or spade.
So, how we got this 13? We divided actually 52 by 4. Because as we explained, for example, how many cards we have which is spade? For example, how many cards that we have which is heart? How many cards that we have which is diamond? There are 13 cards which is diamond. And you know that cards which are diamond, there is ace, there is numbers 2 to 10, there is jack, there is king, there is queen. Therefore, there are 13 cards which are diamond. There are 13 cards which are heart. That's the reason that here we have 13. And this 13 comes from the number of elements, the number of cards which are in one kind. Means the number of cards which are, for example, diamond. The number of cards which are heart. And here, when we say 1, it means that among those numbers which are heart, for example, we choose one of them. Say, for example, among the cards which are heart, we choose, say, king, for example. That's the reason that here we have 13 out of 1. Why do you have 48? Because here in this case, as you can see, you have 1 out of 13. We explain what does it mean. And I want to know that what is 1 out of 48? How I got this? 1 out of 48. How I got 48 actually? How I got 48?
So I need 5 cards. We have already, so first pick a kind, so 13 choose 1. From that kind you choose all 4. And then remaining would be 52 minus 4.
Thank you. What was your name?
AJ.
AJ?
AJ.
AJ, yes, nice to meet you, AJ. So, very good explanation. Thank you, AJ. So, see, you want to pick 5 cards. 4 cards should be in one kind. Say, for example, 4 cards which should be chosen in one kind are chosen. Then what we want to do? Then the remaining is 52 minus 4. 52 minus 4 is 48. In this case, that you have 52 minus 2, 48. That remaining card will be chosen out of this 48. It means in one hand you may have something like this. For example, you may have king of spades. All elements that you have in your hand are king. King of spade, king of heart, king of diamond, blah blah blah. And one remaining, the remaining one should be chosen of the cards that are among the remaining cards. Means 4 cards, which are 4 kings, are already chosen. 52 minus 4 is 48, that one remaining card will be chosen from. Now what about 4 out of 4? 4 out of 4 means that you have 4 cards, because see, in this one, 13 over 1, it means that among, for example, a spade, you will choose king. And then king of all other kinds should be chosen. And this guy is 1. If you do not write this, doesn't matter. And this 1 out of 48 comes from this terminology that you want to choose 5 cards, 4 cards are already chosen, 48 is remaining. Among the remaining cards, you will choose 1 card. And that's the value that we can get for this probability. So, we have other examples. This is another poker example. I don't want to explain about this, that's similar. But something that we should do in the extra credit that you already have is solving some poker problems like these. Then I think if you find those problems a little bit hard, then I think it is good approach that first understand these 2 examples that we have on the slide. I have posted this slide on Carmen. Then you will get a better idea what should be done. So, okay, some formulas that we have about the statistics, we will use them a lot. One of them is statistics, probabilities between 0 and 1. We explained about this before. Probability of negation of an event is 1 minus probability of that event. And this notation means or, probability of A or B is probability of A plus probability of B minus probability of A and B. When we say that probability of A and B means we want to find the probability of the case that events A and B occur simultaneously. And when we want to find the probability of the case that these 2 events occur simultaneously, we will evaluate the probability of A and B. Sometimes instead of A and B, people use the another notation of intersection. Then if you use the notation of intersection, again, you are presenting exactly the same concept. Exactly the same concept. Okay, that's it for basic concepts of probability. Again, if we were too fast, please apologize me. I just want to make sure that this stuff are known for everyone. What is our main goal? Our main goal is use the concept of conditional probability. We will see this semester that, especially in NLP, the concept of conditional probability is used a lot. That's the reason that we want to review this concept. What probability of conditional, what conditional probability means? So for the conditional probability, you want to find the probability of an event by assuming another event already occurs. So then here, in this case, we are interested not in the unconditional probability of rolling, for example, 2 die, but in the conditional posterior probability, or just posterior. For short, we want to find the probability of rolling doubles given that first die is 5. It means, suppose you want to find the probability of, I don't know, a total number of 2 die that you roll is 11. With the condition that the first die shows 5. This kind of probability is called conditional probability. In the conditional probability, we want to find the probability of an event, and we assume that another event already is happened. And that's the way that people write this kind of probability. We use this straight line. This straight line is pronounced given. And here we say that this condition is assumed to happen, and we want to find the probability of this condition. And we will see that in NLP, this concept is very, very helpful. It's very, very helpful, and we will see a little bit about this concept this semester. So then, when we are talking about conditional probability, means that you have 2 events, you want to find the probability of this event with the condition, and this guy already happens. So, so we can use 2 concepts which is used very often to the Bayesian statistics. Some who may be familiar with this concept. We have 2 different types of statistics. traditional statistics and Bayesian statistics, and Bayesian statistics is based on the concept of Bayes' rule that we will see today. In the terminology of Bayesian statistics, we have two concepts, posterior probability and period probability. And here, as you can see, this guy is called the posterior probability, and this guy, which is assumed, is called the period probability. And we will explain about this notation more today. And these are two concepts that I have bold on this slide, and you can see that you have period probability and posterior probability. These concepts are used a lot in Bayesian statistics. We will see today more about this. The formula that we have to evaluate the conditional probability is this formula. Suppose you have A and B, these are two events. B is assumed, and we want to find probability of A. If we want to find such a probability, this is equal to probability of occurring A and B simultaneously divided by the probability of B, which is assumed. So, then for example, if you want to find the probability of double such that die 1 is 5, this is equal to probability of double and die 1 equal 5 over probability of die 1 equal 5. And in this case, as you can see, we assume that this B has the probability bigger than 0 for sure. Okay. One easy example, what is the conditional probability that a family with 2 children has 2 boys, given that at least they have at least 1 boy? Then we want to find the conditional probability that a family with 2 children has 2 boys, given that they have at least 1 boy. If we assume the family has 2 children, all possible outcomes can be listed by using these abbreviations. Here, B stands for boy, G stands for girl. Then both children are boy. The first boy, the second girl, vice versa. First girl, the second boy, and both children are girl. Then in this case, we assume that the chance of boy and girl is equally likely. And in this case, my goal is to find probability of the case that we have. Okay, let me write this. So, yes, our goal is to find the probability of the case that we have 2 boys, such that at least one child is a boy. Then here we can have 2 events. Event A, which contains BB, means both children are boy, and event B, which contains the case that we have at least 1 boy. At least 1 boy means 1 boy or 2 boys. Then we can evaluate this probability by using the formula that we explained in the previous slide. And the probability of A given B is probability of A intersection B over probability of B. If you find the intersection of A and B, then here see intersection of A and B is BB. Probability of BB is 1 over 4. Probability of B is T over 4. When you simplify them, then you will get 1 over T. 1 over 3. These are some basic concepts in statistics, and I just want to make sure all of us are on the same page. We can have very interesting formula which is called product rule in statistics. If you use the cross multiple, then you can say that probability of A intersection B is probability of B times probability of A given B. This is a formula which is used a lot in the concept of Bayes' rule. That is our main goal for today. And statistically, 2 events are called independent if the probability of occurring A and B simultaneously is same as the product of probability of A by B. Okay, so any questions, any comments about this? We have another example here for 3, that's not important. Okay, we are ready to see our main goal to speak, which is the concept of Bayes' rule. For some of you who are more familiar with the statistics, I'm sure that you have seen in other courses that Bayes' rule is used to divide the statistics into 2 different kinds of statistics. The Bayes' rule is a very fundamental concept that we have in statistics. First, I will explain about the formula that we have for the Bayes' rule. So So what do we have in the Bayes? Yes, formula maybe looks a little bit strange, but I just want to explain what we have here. You have two events, say E and F. Your goal is to find the probability of F given E. Something that Bayes rule does gives me the opportunity to switch F and E. That's it. Because see, if you switch this F and E, you will get different conditional probability. Then when you have conditional probability, it matters what event is written before a straight line, what event is written after a straight line. Therefore, if we want to switch them, then we need a tool. Bayes rule is a formula which gives us this ability. Mathematically, the proof of Bayes rule is very easy. But what is interesting, as you can see, when you want to switch this E and F, Bayes rule tells us if you switch them, you have to multiply this by probability of F, and after that, you will write the same thing on the bottom, and same thing this time on the negation of F. Again, I don't want to give you, go to deep statistics, a little bit deeper statistics, but if somebody is interested, this formula comes from the product rule that we had in the previous slide. That's the reason that I'm saying the proof is very easy. It comes from because this guy on the top is nothing other than PE intersection F. This guy PE intersection F, this guy is PE intersection F complement, that's it. And when you take union, then you go and you reach to the same proof. That's very easy proof. But don't worry about the proof. A formula looks, yes please, question?
Sorry, it could be the denominator. Could it be like the probability of E?
In the denominator, we have probability of, yes, exactly. Then this guy that we have here is nothing other than probability of E. And what is it that we have on the top is probability of E intersection.
So why are you writing this so long?
Why are we writing this long way? That's a good question. Because evaluating the probability of intersection in most cases is not easy. But this guy tools me, this guy gives me the tool to evaluate the probability of this by using conditional. You will see that in examples. Evaluating the probability of this product is easier than evaluating the probability of intersection. Intersection is a kind of bad behaved operation comparing to the conditional. That's the reason that product rule that we had in the previous slide is very helpful. That's the reason that people write in this way. Mathematically, something that we have here is nothing. This is intersection, this is probability of. But why we wrote in such particular stuff? Because we will see that in most cases, because see, that's something that we are learning here. In most cases, we do not have the case that probability of one event is probability of every event which is even is based on some conditions. Therefore, formula which can be used to convert the probability of one event into probability of some conditions is helpful. That's exactly something that we do. And very, very interesting formula actually. Bayes rule is very interesting. First, when I saw Bayes rule, I think I was about to finish high school. I found it very interesting. That's very interesting. Okay, and in this case, as you can see, we have just two cases. We can have more than two cases. I just want to recall you one formula, probability. When you have negation on after arrow or before arrow, we have a different situation. If you have negation after arrow, nothing can be done. But when you have negation before arrow, you can get rid of negation by subtracting from 1. And now 1 minus. But before arrow, let's see, after arrow, nothing can be done. Before arrow, we have this formula. You can get rid of negation. Okay, I understand. If you have not seen this formula before and it is the first time that you see this formula, it looks terrible. Let me give you one example to show you what should be done, how this formula should be used. And you have two examples similar to this problem in your extra credit. Suppose that one person in 100,000 has a particular rare disease for which there is a fairly accurate diagnostic test. This test is correct 99% of the time when given to a person selected at random who has the disease. It is also correct 99.5% of the time when given to a person selected at random who does not have the disease. Let me explain what does it mean when we say that it is correct. It means that if we have a person who has the disease, the test also comes positive. If we have, and when we say that given to the person which doesn't have the disease, means that if the person doesn't have the disease, the test also comes negative. This is a technique which is used a lot because see, you have a test, for example, test for a disease. You want to check the sensitivity of this test. In what scenario the sensitivity will be evaluated? We want to see that in how many cases the person who has the disease, his test also comes positive, and in how many cases the person who doesn't have the disease, the test comes negative. And here when we say that 99%, when the person given test to the person who has the disease, the test is accurate, means that the person has the disease and test comes positive. In 99% of the time, this may happen. And in 99.5% of the time, you give the test to the person who doesn't have the disease and test comes negative. That's the notation which is used in a statistic as the correct negative, correct positive, or true negative, true positive. Make sense? Make sense? Questions, comments? So, now let's find this probability. Find the probability that a person who tests positive for the disease has the disease. And find the probability that a person who tests negative for the disease does not have the disease. So, my goal here is to find the probability that if a person who tests negative really has the disease. Please remember that these 99 and 99.5% are the opposite directions. Let me explain. We will use some notations. Let E be the proposition that the person's test is positive, and F be the proposition that this person has the disease. Let's see here we have two cases. E is the proposition that the person's test comes positive, and F is the proposition that this person has the disease. What is the sensitivity? Sensitivity is this. If the person has the disease, test comes positive. See? If the person has the disease, test comes positive. This probability is 99%. If the person has the disease, test comes positive. And what about the negative side? If the person doesn't have the disease, test comes negative. This one is 99.5%. Our goal is to find what? Then say opposite direction. It means you want to find the probability that if the person, then see if the test comes positive, the person has the disease. Everybody's following what I'm saying? Then see the sensitivity of the test, which was given in the previous slide, can be formulated mathematically in this way. That you can say that the sensitivity means if the person has the disease, test comes positive. We want to find the opposite direction. We want to find if the test comes positive, what is the probability that the person has the disease? Any questions? Any comments? In this case, Bayes' rule can be used very nicely because you have this probability, but you want to find the probability of the case that you switch E and F. Therefore, Bayes' rule is used to give us this ability. In order to use Bayes' rule, we have to, that's the Bayes' rule. My goal is to find this probability. By using Bayes' rule, it can be written in this way. And then the values which are given will be plugged in the formula. For example, this guy is given, I plug in the formula. What is P of F? What was F? F is the person. F is the proposition that the person has the disease. We know what is this probability because as we explained in the previous slide, in this disease, 1 out of 100,000 people has this disease. Therefore, the probability of the case that one person has this disease is this guy. I wrote exactly the same thing in the denominator. What about this guy? For this guy, you want to find probability of E given negation of F. I do not have this, but I have this guy. Since I want to get rid of this negation, then this formula can be used. I want to find the probability of E given negation of F by using the formula that we had in the previous slide. If you want to get rid of this negation, you just do subtract. And when we subtract, we get this number. That's the number that we want. And how I got probability of negation of F, when you have the probability of F is this number, you just need to subtract this number from 1 and get this number. And we evaluate and we get this value. This is one good example which shows us how Bayes rule can be used. In extracurricular problem, you have two problems completely similar to this. I think before solving that problem, it will be very helpful if you understand this example, then solve that problem. For the part 2, we want to find the probability of the case that, because probability of negation E given negation of F is given. I mean, we want to find this probability again, Bayes rule can be used, and very easy example. As you can see, the probability of the case that the person, the test comes negative, the probability of the case that, because here my goal is to find the probability of negation of F given negation of E, means that if the test comes negative, what is the probability of the case that the person doesn't have the disease? That's the probability that we have. And very high chance. Okay, for the case that you have more than one propositions, it means that if you want to extend Bayes rule for the cases that you have more than two cases in the denominator, this formula can be written. I do not want to go very deep about this formula, just like in two cases that we had in the previous slides are enough for us. Okay, so hope our review wasn't too quick, and hope I did not drown you in the formulas. For some of you, sorry about that. So for some of you who have seen this stuff before, maybe it was boring. For some of you who haven't seen this stuff before, maybe it was a little bit challenging. If you find these formulas challenging, these concepts challenging, that's perfectly understandable. Don't worry about this, don't panic. And if you find this stuff boring, I'm sorry. I just wanted to make sure all of us are in the same page. What should be done to understand these concepts better? Please try to solve extracurricular problem intentionally. I gave you that problem. Because in the class, we do not want to spend our time on these concepts. We have something more interesting to teach. Then I'll be available in office for some of you who need my help to solve extracurricular problem. I'll be more than happy to help. Please stop by. And my main goal for this extracurricular is to make sure everybody understands the formula that we have in this slide. These concepts will be used a lot in statistics and in machine learning. For some of you who have seen machine learning before, then I'm sure that you have seen these concepts. Okay, so after this kind of review, let's come back to our main goal, which is using concept of Bayes rule for defining a new classifier. That's actually our main goal, for a new classifier, which is called naive Bayes classifier. So then let's see what is our goal. I want to fix some notations that we will explain about today are very popular notations in machine learning. So then let's see what we have here. Our goal is to determine the best hypothesis given data type. When the best hypothesis means the most probable hypothesis given data type. and any initial knowledge period probability of a various hypothesis. Something that we want to do here is to find the best hypothesis by using the data. Let me explain what does it mean when we say that best hypothesis. Suppose a person comes and we test that person for a disease. We want to, the test shows positive. We want to evaluate the chance that this positivity is accurate. That's what we want to do. It means we want to see that what hypothesis has the more probable. When we say that what hypothesis has the most probable, the probability of which hypothesis is the higher, means that if you have two hypotheses, which is the person has the disease, the person doesn't have the disease, we want to see that which one has the higher probability. That's what we want to do here. In what way these hypotheses can be checked? By using data. Therefore, in order to answer that question that we had at the beginning of our class, why conditional probability is important? Because in most cases, when we want to check a hypothesis, this checking of hypothesis can be done by using the data. Therefore, in most cases, something that we do is finding this probability. Means we want to find the probability of H given data. That's a very, very popular notation in machine learning. In machine learning, something that we do always is checking a hypothesis. So you have a set of hypotheses, and you want to check which hypothesis has the highest probability. But how you can check that hypothesis? By using data. Therefore, the conditional probability that we explained very fast today is very popular in machine learning. Mathematical this notation can be written in this way. We have on max H PhD, then if I explain what it means that you want to find the hypothesis for which this probability gets maximum. Then hope this notation makes sense. If it doesn't, it has very popular notation in machine learning. When you want to write something like this, it means you want to find hypothesis for which this probability is maximum. Notations make sense, questions, comments. Please don't be shy. If you haven't seen notation, the notation is hard. Please ask, please don't be shy. Any questions, any comments? Any questions? Question? So, Bayes theorem can be used in this. Let's see, my goal is to find probability of H given data. Means we want to test a hypothesis by using data. Sadly, this probability cannot be evaluated because the probability is available is this kind. Means you can, by assuming a hypothesis, we can find the probability of data. For example, by assuming that the person has disease, we can find the probability of data, but this guy cannot be evaluated. Then, as you can see, Bayes theorem can be used very nicely because Bayes theorem gives us the tool for switching H and D. Then Bayes theorem tells us this PH given data is equal to PD given H times P of H over P of D. What is P of D? Is this one? Yes, I understand this probably looks terrible, but don't worry about this because always P of D is constant, and since you want to maximize this, then you don't need to worry about denominator. The only thing that you need to worry about is numerator. There are some terminology here which are used a lot. First, P of H is called period. That's the information, that is the period information about hypothesis. And posterior, this guy is posterior. Your goal is to find the period, the probability of posterior by using the probability of period. What about this guy? That's called likelihood. And P of D, as I explained, is a constant always. Then if this formula looks hard, you can ignore the denominator. Based on my experience, I taught this in 2 states. Then based on my experience, most of the students find this denominator which is given based on the sigma theorem, but don't worry about this, you don't need to worry about this because that's constant. we will see that the only thing that we need to care about is top, numerator, because denominator is constant. Again, if notations looks as strange, we will make it more understandable by solving homework. That's very understandable to me if you find notations as strange, especially if you haven't seen this before. Notations look as strange. That's very understandable. But I just want to explain about names, that this guy is called posterior, this guy is called period, this guy is called likelihood. And denominator doesn't matter because that is a constant. Okay, so a little bit, one example, maybe we cannot finish this example completely today, but that's a very good example to help us to understand the notations that we had in the previous slide better. Suppose the following information about the patient is given. Our goal is to determine if this person has cancer or not. Before continuing about this, guys, I told them, I taught this slide in 2 states. It happened to me that some students feel pissed off. I understand that you're talking about cancer is painful, and I'm sorry, that's just for educational purposes. And if you find this, painful, that's understandable. All of us have a bad memory about this. My family is a history of cancer, many cancers in my family. That's very understandable to me if you find it bad, but I hope these concepts using cancer and all this stuff doesn't piss anyone off. Then if you find it painful, I'm so sorry. Okay, so now I can explain about the concept, about the notations that we had in the previous slide. Do you remember what I told you? Our goal is to test hypotheses. What does it mean? Hypothesis means that a person comes for testing. We want to know that if this person has cancer or doesn't have cancer. Then my hypothesis, how many hypotheses do I have? 2 hypotheses. The person has cancer, unfortunately, or the person doesn't have cancer. See? Then the set of hypotheses for this example contains 2 outcomes. The person has cancer, the person doesn't have cancer. And we want to test for this hypothesis. Yes? In what way we can test this hypothesis? Only God of these words can say, if you see me. Before testing me, you cannot say if I have cancer or I don't have cancer. Therefore, we need to use data. In what way data can be used? We have the data about the test that we are using on this patient. Data comes here, for example. Here we have 2 notation, positive test for cancer, positive, negative for test for cancer is negative. These are the data that we have. Probability of a person who has been chosen randomly has the cancer is this. Then the probability of the case that the person doesn't have cancer is 1 minus this. Right? See, these are data. Do you understand what I'm saying? Then this is very important. I have chosen this example actually. Durability. I checked many examples when I wanted to teach this first, because this example is a very good example to make notations that we had in the previous slide more understandable. See, your goal is to test for hypothesis. The person has cancer, the person doesn't have cancer. And you will use data. See, it comes from data. The probability of one person which has been chosen randomly has the cancer, it comes from data. This guy comes from data. See, these probabilities come from data. So, this is the case that we have. If the person has, because I am using one test on this patient, that's the sensitivity of this test. If the person has cancer, probability of the test shows positive. That's the number. Again, it comes from data. If the person has cancer, test comes negative. This guy comes from this minus 1. See how I got this guy? I subtracted 0.98 from 1, I got 0.02. This guy also comes from sensitivity of the test. If the person doesn't have cancer, the test comes negative, 0.97. And this guy again comes from subtracting this from 1. Then see, the value that you have here comes from data. The value that you have here comes from data. Do you see now what I said? Our goal is to find probability of the person has cancer if the test comes positive. Because see, let me explain these on the board. If you understand this, then see, because I taught Bayesian statistics, in my Bayesian statistics classes, also I teach this example when I want to start the concept based on my experience. If most students, when they understand this example, they understand notations very well. See, what is then hypothesis here, set of hypotheses, is the person has cancer, the person doesn't have cancer, doesn't have cancer, doesn't have cancer. These are hypotheses. I will denote this guy by, say, H. This guy is negation of H. You want to check to see that which one has the higher probability. What we will do, then see, that's what we do. We want to find the probability of H given D. That is data, that is hypothesis. More precisely, we want to find that probability of person has cancer, it is given a data. This guy cannot be evaluated. Then it means that when we want to find, then we to see which of these hypotheses should be accepted, we will evaluate these two probabilities. This probability and this probability. And we will pick the one which has the higher probability. Means if this guy has the higher probability, we would say the person has cancer. If this guy has the higher probability, we would say the person doesn't have cancer. Right? But the problem is that this probability is not available. But if you switch these, the probability is available. When we switch, it means if we have probability of D given H. It means what? It means, for example, because see, this D data that we have here comes from test. It means, for example, test is positive, person has cancer. Probability of the case that test is positive, person has cancer. In this case, this probability is not known, but if we switch them, means if we want to find the probability of positive, if the person has cancer, this probability is available. It comes from the sensitivity of the data. Therefore, Bayes formula can be used here. Because Bayes formula is a tool to help us to switch these two. And that's exactly something that we want to do in this example. Any questions? Any comments? Silence means it is understandable or silence? But based on my experience, silence usually has two meanings. Everybody understands, nobody understands. Mostly the second one. Nobody understands. Something which is strange to me is the case that nobody understands and nobody cares. That's very interesting. Nobody cares. So, my wife has a very interesting ability. When she goes to a class and somebody teaches her, if she doesn't understand, she just writes. And that is something I can't do at all. When I was a student, I remember that in undergrad and in high school. If I did not understand something, I stopped writing. Something more interesting, if somebody teaches something that I didn't like, again, I stop writing. Never something which happened, I didn't like geography, and I was studying for the exam for geography. There was some stuff about geography that I found them very terrible. I didn't want to even learn them. And I didn't learn them, I went to the exam. I failed. But my wife never does something like this. I think that's interesting. Okay, so guys, hope this stuff makes notations more understandable. Notations that we have in the previous slide, which is very popular notation in Bayesian statistic terminology, is a little bit strange. And if you find it strange, it's very understandable. Then you just need to understand what is hypothesis, what is data. Everything which comes from test is data. Then here, when we say that positive, negative, this stuff comes from test. This is stuff or data. And remember that, let's come back to the previous slide. Your goal is to find probability of H given data. But this probability is not available, but this guy is available. Means the case that we say that the hypothesis is assumed, what will happen in our data. This is something that we have here. See, you assume the hypothesis of the person has cancer is assumed, and you want to see that what is the probability that your test also comes positive. This information is available. That's the sensitivity of test. You assume that the person doesn't have cancer and test comes negative. This one also sensitivity of the test is also available. Okay, so then now we observe a new patient with positive test results. Should we diagnose this person as having cancer or not? Again, see, your hypothesis is what? Is that we want to see that we should diagnose this person as a person who has a cancer, or diagnose the person as the patient who doesn't have cancer. That's what we want to do here. Then see, this first one comes from data, because you assume that the new patient comes, test comes positive. See, it comes from data. You want to know that we should diagnose this person as cancer or not cancer. See, this is hypothesis. But then my goal is to find this probability. Again, data hypothesis. The person test of this guy comes positive. My goal is to find the probability of this person has cancer. Then two probabilities should be evaluated. The probability of the case that the person has cancer when test comes positive. Probability of the case that the person doesn't have cancer when test comes positive. Among them, the one which has the higher probability is the one which is used for diagnosing. So, since this guy cannot be evaluated, we will use Bayes formula. Bayes formula tells us if you want to switch these two, switch it, but multiply by the probability of period. What about denominator? Because remember that in the Bayes formula, we have a terrible denominator, but don't worry about denominator, because that denominator is constant. Since you want to maximize this, just numerator matters. So then that's the period probability, that's the likelihood. You multiply them and you will find the probability. For the case that the person has cancer, the person doesn't have cancer. This is for the case that the person has cancer and test comes positive. The person doesn't have cancer, test comes positive. And these are the probability of H and negation of H. We evaluate them, then we got these two numbers. Then which one is bigger? This guy is bigger. And what we can say that fortunately the person doesn't have cancer. Then we diagnose the person as no cancer, although test comes positive. Any questions, any comments? Let's see. Calculation, because again, when I teach usually in my Bayesian classes, most of the students says, oh, that's a very easy calculation. Yes, it is. That's easy calculation. What is important, this Bayes formula that you are learning now is not hard. Based on my experience of teaching this several times, is that because notations look strange, students find it awkward, especially if you haven't seen this in other classes before, you may find it very awkward. You just need to understand what hypothesis means, what data means. This is a very good example. Again, I told you I have a story, this example from somewhere, I don't remember where, it was a long time ago. But I checked many books, many websites to find this example when I wanted to teach this first, because this example shows very well what data and hypothesis means. See, hypothesis means we want to diagnose the person as has cancer or doesn't have cancer. This is hypothesis. The person has cancer, the person doesn't have cancer. I want to emphasize on this word. I am testing for that hypothesis. For some of you who have the background in statistics, you know that hypothesis test is one tool that we have in statistics. We test hypothesis. That's what we do here. In what way hypothesis is tested? Hypothesis in statistics is tested based on the data. From where we get data? From tests. It means that you have, for example, a test on a patient, And whatever that you say about test means the test of this guy comes positive, the test of this guy comes negative, this is stuff related to your data. Then here, as you can see, I am testing the hypothesis of the person has cancer or doesn't have cancer on the available data. Then we compare these two probabilities. The one which has maximum will give us the diagnosis that we can make. Okay, I think it is good time to stop. If I'm sure that for some of you class was a little bit strange with lots of formulas. For some of you it was boring. I'm sorry. I apologize for both groups. But I just want to make sure that all of us are in the same page. Please finish extra liquidity number 1 and return it in class on Thursday or be available in office. Any questions, anything, please feel free to stop by. And have a good day. See you all on Thursday.